Tonight, the quiet between the stars is broken by a traveler. It does not announce itself with radio greetings or flashing lights. Instead, it slips into our sky as a dim, persistent smear of light, first noticed by careful eyes in early July. Within days of its discovery, sensational headlines crackled. Some called it a cosmic threat, others murmured about alien technology. But the truth of this visitor is far more intriguing than any science fiction. It is Comet 3I Atlas, only the third interstellar object ever seen passing through our solar system. Born under another sun and now writing a brief glowing line across our sky, it will soon vanish back into the darkness between the stars, perhaps forever. To grasp the wonder of this moment, imagine walking along a beach and finding a piece of driftwood that you realize came from a faraway, unknown shore. That is what this comet represents to us. It is a fragment of a distant world, shaped by a star that is not our own, carrying chemical clues that whisper of a place we will likely never visit. For a few precious months, this lost traveler belongs to us, an object from an alien ocean of stars, now washed up in our cosmic front yard for study. The discovery itself was sudden and electrifying. Late on the night of July 1st, 2025, an automated telescope in Rio Hurtado, Chile, part of the Atlas Sky Survey, captured images of a faint point of light moving in an odd way. Initially, it looked like just another small comet or asteroid, but something didn't fit. Its path on the sky didn't align with the usual orbits of objects bound to our sun. As astronomers around the world received the alert and ran the numbers, excitement grew to a fever pitch. New observations poured in over the next days, and when those were compared with older archival images, some going back to mid-June, the verdict became clear and astonishing. This object was not orbiting the sun at all. It was on a one-way trip. In other words, its trajectory was what we call hyperbolic, meaning it is not bound by the sun's gravity and will not circle back. It came from the depths of interstellar space and will head right back out into the void. The Minor Planet Center quickly designated it 3I, the third interstellar object. Hyperbolic is a technical term, but we can picture it vividly. Imagine the sun as a great boulder sitting in the middle of a river, and the traveler as a leaf carried by the current. Most leaves, like most comets and asteroids we know, get caught in swirling eddies around the boulder. These are the closed, looping orbits that bind ordinary objects to the sun, such as planets circling in ellipses or periodic comets coming and going on elongated loops. But a few rare leaves zoom straight in with the current, brush past the boulder, and then slip back out to continue downstream. That one-time swoop around the boulder is a hyperbola. The path doesn't close into a loop. It opens out and never returns. The instant astronomers saw the math of its path, they knew this visitor was not local. It wasn't born here, and it would not stay. Tracing the incoming trajectory, the interstellar visitor appears to have come from the direction of the constellation Sagittarius, roughly toward the dense star fields near the center of our Milky Way galaxy. It approached our solar system at a blistering speed of tens of kilometers per second, faster than any rocket humanity has ever launched, fast enough that it could travel from Earth to the Moon in just a couple of hours. Speeds like that are a telltale signature of an object unbound by our sun. Such velocity hints at a powerful slingshot in its past, perhaps long ago. A jostling dance with a giant planet in its home system flung it outward, or maybe the cumulative nudge of passing stars over eons gradually kicked it to escape velocity. However it happened, at some point in the distant past, the object was evicted from its native star system's gravitational embrace and sent careening into the interstellar void. It may have wandered alone for millions or even billions of years before fate brought it near our sun. One can't help but wonder about that original home. Perhaps it was a dim red dwarf star in a quiet corner of the galaxy, encircled by a cold disk of dust and ice. In that faraway system's infancy, ATLAS might have formed from the same protoplanetary disk that made its planets. It could have spent eons as a frozen body on the fringe of that system, like how our own comets dwell in the distant Oort cloud, until some cosmic disturbance set it free. Maybe a passing star came too close, or a giant planet migrated and gravitationally catapulted the little comet outward. From that moment on, it became an interstellar drifter. Try to imagine the long solitude of such a journey, drifting in the darkness between stars, far from any sun's warm glow, for longer than human civilization has existed. For ages, it was just another tiny, silent ice ball among the stars. Then, by incredible chance, its path and our solar system's path intersected. This year, Earth's telescopes caught the faint glimmer of that ancient wanderer as it finally encountered the light and gravity of a new star. Ours. The C in its formal designation stands for comet, and that one letter carries a lot of significance. It means that Atlas isn't just a bare rock. It's an icy body that can sprout a coma and tail when warmed. Comets are often described as time capsules because they preserve the primitive materials, ices, dust, and organic compounds from the dawn of their star systems. They are cosmic freezers, keeping ancient secrets on ice. As soon as Atlas was identified, telescopes, big and small, swung toward it to see if it would behave like a comet. The early observations did not disappoint. By the time it was discovered inbound, the comet was already showing a faint coma, a delicate mist of gas and dust evaporating from its nucleus as sunlight started to heat it up. Make no mistake, 3IATLAS was no great spectacle to the naked eye. There were no dramatic sky-filling tails or bright flares visible without instruments. This was a subtle, ghostly halo, detectable only by sensitive cameras and experienced observers. It was the quiet breathing of a small, icy world waking up for the first time in the warmth of an unfamiliar sun. If you've ever left a freezer pack out on a warm day and watched frost on its surface disappear into vapor, you have a tiny sense of what was happening to 3IATLAS. The process is called outgassing. Sunlight penetrates the comet's surface, and frozen gases buried in the ice begin to sublimate, turn directly from solid to gas, escaping into space and dragging out dust particles with them. This forms a hazy cloud around the solid nucleus, the coma, and often a tail that streams away from the sun due to the pressure of sunlight and the solar wind. In late 2025, Atlas had begun to exhale its ancient ices. We were able to sniff those gases using our most powerful telescopes and instruments, including the new James Webb Space Telescope. What we found when we dispersed the comet's light into a spectrum, like spreading sunlight into a rainbow to see the colors, was surprising and fascinating. The coma of ATLAS turned out to have an unusual chemical signature. By looking at the specific colors of light absorbed and emitted by the gas around the comet, astronomers determined that this comet is rich in carbon dioxide gas, with comparatively modest amounts of water vapor. In fact, measurements suggest it was releasing roughly 8 times more carbon dioxide than water. This is striking because most comets that venture into the inner regions of our solar system tend to produce copious water vapor as they heat up, since water ice is a major component of their makeup. Carbon dioxide is present in many comets too, but usually as a smaller fraction that becomes noticeable only when the comet is far enough from the sun that water stays mostly frozen. But here is 3I Atlas, a visitor from another star, flaunting a coma dominated by carbon dioxide early in its approach. What could this mean? One implication is that Atlas might have formed in a very cold region of its home system. perhaps out near that system's equivalent of a Kuiper belt or beyond, where carbon dioxide ice, which is more volatile, meaning it turns to gas at lower temperatures than water ice does, could accumulate in large quantities. It might be a clue that in the chemistry of its original nursery, carbon dioxide was especially abundant, or that the comet stayed so cold for so long that much of its water remained locked away beneath the surface. Another possibility scientists have proposed is that during the comet's long journey through interstellar space, exposure to cosmic rays and high-energy particles could have altered the layers of ice on its surface. Over millions of years, this radiation can trigger chemical reactions that form a kind of crust of complex organics on the surface, effectively sealing in some of the water ice below. Meanwhile, more volatile substances like carbon dioxide and carbon monoxide, which don't freeze as hard, might be closer to the surface or trapped in that crust, ready to burst out once the comet approaches a star. Thus, when Atlas started warming up near our Sun, the carbon dioxide was the first to escape in large volumes, whereas water vapor began to emerge more slowly as the Sun's heat dug deeper into the comet's layers. And CO2 wasn't the only thing coming out. Other ingredients made their presence known as well. Telescopes detected a modest but measurable amount of carbon monoxide in the coma. There were also signatures of cyanide gas, a common tracer in cometary comas that glows in a characteristic way and often helps astronomers estimate how active a comet is. Perhaps most intriguingly, some observations even picked up hints of heavy elements like nickel in the vapor. In recent years, scientists have discovered that many comets, even our familiar ones, release tiny amounts of metals such as iron and nickel when they are near the Sun, likely because there are fragile organic compounds or metallized dust grains that break apart under solar heat and ultraviolet radiation, freeing metal atoms. Atlas, it turns out, follows this curious pattern too, showing that even a comet from another star shares this trait. All these chemical fingerprints, the gases and elements we've identified, place 3I Atlas in a curious middle ground. In some ways, it feels like a cousin to the comets we know. It has common molecules like water, carbon monoxide, and cyanide, and even the odd nickel vapor that we've come to recognize in cometary comas. Yet the proportions are different enough to remind us that this object was cooked in a different kitchen. Around another star, nature baked a comet with its own recipe, using the same basic ingredients but in different measures. Studying those differences is like comparing a recipe from a foreign cuisine. It tells us about the environment and history of that distant place. After the initial frenzy of discovery, astronomers worldwide settled in to observe 3 IAT LAS as thoroughly as possible during its fleeting visit. The comet's path was calculated with increasing precision. It was determined that Atlas would make its closest approach to the Sun, its perihelion, in late October 2025, swinging inside the orbit of Mars at about 1.4 astronomical units from the Sun. 1 astronomical unit, or AU, is the distance between Earth and the Sun. That distance is roughly 210 million kilometers, far closer to the Sun than Earth is, but still a good bit farther out than our planet. After perihelion, the comet would head back outwards, crossing the plane of Earth's orbit in December. Importantly, it was never going to come particularly close to Earth. The closest it would get to our planet would be on its way out in mid-December 2025, at a distance of about 270 million kilometers, or hundreds of millions of miles away. In celestial terms, that's a wide berth, comfortingly far, as some might say. So there was never any danger of a collision, and no need for the public to worry about doomsday impacts, despite some of those early breathless headlines. For most casual skywatchers, ATLAS would remain an elusive target. Even at its brightest, it was not expected to reach naked eye visibility. Only large telescopes or long exposure photographs from amateur astronomers with good equipment would show it as a tiny smudge moving against the starry background. But for professional astronomers, the geometry of its visit was a golden opportunity. The comet approached from the southern sky and was observable from Earth-based telescopes through much of the approach, July through September. Although it disappeared behind the glare of the sun around the time of its October perihelion, making it temporarily unobservable from Earth's night side, it was picked up again afterwards as it emerged into the morning skies of late November and December. This meant we got a nearly continuous record of observations, from when it was first discovered in the outer solar system, all the way through its closest swing by the sun, and as it began its exit journey. Multiple powerful observatories contributed to this unprecedented portrait of an interstellar interloper. On the ground, facilities like the Gemini South Telescope in Chile and the Southern African Large Telescope gathered spectroscopic data and images, dissecting the coma's light for clues to its makeup. NASA's Hubble Space Telescope, ever sharp-eyed, managed to capture images of Atlas as well. On July 21, 2025, Hubble snapped a picture of the comet when it was about 277 million miles from Earth. In that image, the comet appears as a tiny teardrop-shaped cocoon of light, the diffuse glow of dust being shed from the icy nucleus. Because Hubble was tracking the moving comet, the background stars appeared as streaks. That teardrop glow told astronomers that dust was actively coming off the nucleus. And from such observations, they started to estimate how big the solid nucleus might be. By August, Hubble's data suggested the nucleus could be at most around 5 or 6 kilometers in diameter, and possibly as small as 500 meters or so. In other words, Atlas is probably a modest-sized comet. Not a giant by solar system standards, but not tiny either. It falls somewhere between the size of a city and a small mountain. That is more or less in line with the sizes of comets we're familiar with. So again, it's extraordinary in where it came from, but not so extraordinary in its physical size. Meanwhile, the brand new James Webb Space Telescope took advantage of its infrared vision to study the comet's composition, measuring the gases and even searching for complex molecules. Other space-based observatories joined the effort. NASA's Swift Telescope, usually hunting distant gamma-ray bursts, observed the comet's ultraviolet glow. The transiting exoplanet survey satellite even took time away from scanning for exoplanets to monitor the comet's brightness changes over several weeks, which helped reduce its rotation period. Astronomers determined that 3I Atlas rotates roughly once every 16 hours, a leisurely spin for a cometary nucleus. Closer to the Sun, NASA's solar observatories like SOHO and Parker Solar Probe kept watch to see if the comet would become visible as it neared perihelion. Indeed, SOHO's coronagraph, a device that blocks out the Sun's disk to spot faint objects nearby, caught a tiny speck of light as it skirted past the Sun in late October. Even spacecraft not originally intended for comet observations pitched in. As Atlas slipped past the orbit of Mars, humanity's robotic emissaries around the red planet turned their cameras skyward. The European Space Agency's ExoMars Trace Gas Orbiter and Mars Express spacecraft attempted to photograph the comet when it was closest to Mars, about 29 million kilometers from the planet on October 3, 2025. Against all odds, ExoMars TGO managed to capture an image. The comet appeared as nothing more than a slightly fuzzy white dot among streaks of distant stars. But that faint dot was history in the making, a visitor from another star seen from a vantage point around another world. These efforts demonstrated how keen we were to observe every moment of this visitor's journey. The result is a remarkable and nearly uninterrupted record of an interstellar object's behavior as it interacted with a star. From the far reaches of the solar system, through its perihelion heating, and onward as it receded, we have followed 3 IATLAS with unprecedented thoroughness. By comparison, the first interstellar object 1I Oumuamua was spotted only after it had already made its closest pass to the Sun and was heading out, giving us very limited time to observe it. And 2I Borisov, while observed during its approach and departure in 2019 to 2020, did not benefit from quite the same array of telescopes and instruments as we have now in 2025. With 3 IATLAS, humanity threw essentially everything we had at it, from big ground observatories to space telescopes to even planetary probes. And the comet rewarded us with a treasure of data, as well as a few puzzles to chew on. If all of this feels faintly familiar, it might be because you recall the excitement of 1I Oumuamua back in 2017 and 2I Borisov in 2019. Those were our first 2 interstellar interlopers. Each taught us different lessons. Oumuamua, the name means scout in Hawaiian, was highly enigmatic. It was small, perhaps only a few hundred meters long, and had no detectable coma. Yet it exhibited a strange non-gravitational acceleration, as if something was gently pushing it outward faster than the Sun's gravity alone would account for. Scientists proposed various explanations, from outgassing of hydrogen or other invisible molecules to more exotic ideas, like it being a lightweight light sail engineered by aliens catching the sunlight. The lack of data, it was seen only briefly, meant that debate about Oumuamua's true nature went on for years and is probably still not fully settled. It was unlike any comet or asteroid seen before, and its odd behavior truly stretched our imagination. Then came 2I Borisov, discovered in late 2019 by an amateur astronomer in Crimea. Borisov was a breath of fresh air for astronomers because it was, in most respects, just like a normal comet from our solar system. It had a fuzzy coma, a tail, and a composition that, while showing some noteworthy differences, for instance, an unusually high amount of carbon monoxide relative to water ice, hinting it too came from a very cold place, did not defy expectations the way Oumuamua did. Borisov essentially confirmed that the galaxy is likely teeming with icy comets that have been kicked out of their home systems and wander the stars, and that at least some of those that pass near us will look and behave a lot like the comets we've known all along. If Oumuamua was the bizarre outsider that sparked wild theories, Borisov was the reassuring cousin from out of town. Now this visitor sits closer to Borisov on that spectrum. Like Borisov, the comet clearly behaves like one. It has active outgassing, a coma, and a tail, albeit a faint one. We can directly measure its gases, and its trajectory is well behaved aside from the slight push that Cometary outgassing can give. And as of now, there has been no drastic unexplained acceleration beyond that. In many ways, it has calmed the waters of speculation that Oumuamua stirred up. There is no need to invoke alien technology to explain anything about it. Its mysteries are within the realm of natural comet physics. Yet this traveler is also more extreme in its path and speed than either of its predecessors. It came barreling in on a steep incline relative to the plane of our solar system's planets, and it will depart at a high velocity as well. It is as if it had a longer run-up before reaching us, meaning it might have been traveling for a very long time or fallen from a higher above the plane orbit in our galaxy's disk. What all three of these interstellar visitors have done is expand our sense of what is out there. They are three data points, hinting at a vast population of objects that drift between the stars. Some might be bizarre shards of fractured worlds. Some might be pristine comets that never got close to their parent suns. Some could be rocky asteroids, and others truly exotic icy mixtures. We have learned that interstellar objects can be icy like comets, and perhaps rocky like asteroids, and they can occasionally masquerade as one another, with Oumuamua blurring that line. Each new object is a chance to refine our understanding, and also to stoke our imagination about what might roam the dark spaces between solar systems. Inevitably, whenever a mysterious object from beyond appears, whispers follow. Could it be an alien spacecraft? Is there a cover-up or some deeper significance that authorities are not sharing? This case was no exception. On internet forums and social media, a few voices speculated wildly. Perhaps this comet was actually a disguised probe sent by an extraterrestrial civilization. Or maybe its trajectory was intentionally aimed as a message or a surveillance mission. Others spun conspiracy theories that a secret planetary defense alert had been triggered and governments were hiding a potential threat. In truth, a small object on a distant trajectory can light up imaginations precisely because it is unknown and comes from outside our familiar neighborhood. We humans are storytellers, and sometimes we let our speculation run ahead of the facts. But a little skepticism, combined with a lot of solid data, goes a long way to dispel these dramatic notions. There is no evidence of any artificial behavior from this body. If one looks at the details of its movement and changes in brightness, everything lines up with normal comet physics. The fluctuations in its brightness can be correlated with bursts of outgassing, sunlight causing pockets of ice to vaporize and vent gas, not the controlled thrust of engines. The material shedding from it forms a diffuse tail, exactly as we would expect from dust pushed by solar radiation, not a tight plume or any pattern suggestive of machinery. Its trajectory, while extraordinary in origin, is exactly what gravity dictates, given its speed and incoming direction. It was not decelerating or adjusting course in any unnatural way. In short, the object behaved every bit like a small natural world being gently steered by gravity and physics, with no hints of technology or intent. As for the idea of a planetary defense alert, there is a grain of truth that got twisted. Yes, the planetary defense community, the global network of scientists and space agencies who work on detecting and responding to asteroid and comet hazards, did pay very close attention to the comet, but not because it posed a danger. Instead, they saw it as a perfect training exercise. Think of it like a fire drill. You do not wait for a real fire to practice your escape route. In the same way, our asteroid tracking and defense networks use this harmless interstellar visitor as a chance to test their coordination and observation skills. Teams around the globe coordinated to track its position very precisely to see how well and how quickly they could pin down the orbit of a fast-moving new object. They practiced rapidly sharing data and refining predictions of its path. Techniques that would be essential if, someday, we found a comet on a collision course with Earth. By surrounding this visitor with instruments and monitoring its every move, they essentially treated it like a potentially hazardous comet in a mock scenario, which allowed them to identify any weaknesses in our global preparedness. Fortunately, the visitor itself was utterly benign, and turning a once-in-a-lifetime guest into a training target is exactly the kind of preparation we want before a real threat ever appears. There was nothing secret about it. The effort was openly discussed in scientific circles and hailed as a successful demonstration of international collaboration. This is where the story of the comet intersects with the broader story of how we watch the skies. The Atlas survey that found it runs every clear night, catching faint movers against a crowded sky. It is part of a new era of all-sky vigilance. In the past, discovering a comet or asteroid often relied on skilled individuals or scattered programs. Now, we have automated systems like Atlas, with eyes in both hemispheres, that are dedicated to catching the slightest winks of moving light against the starry backdrop. And soon, the Verisi Rubin Observatory in Chile, with its powerful telescope and gigantic camera, will come online and repeatedly survey the entire night sky in unprecedented detail. Once the Rubin Observatory begins full operations, we expect to find many more interstellar objects, perhaps even several each year, simply because we will finally be looking with the right sensitivity and frequency to catch these fast-moving faint visitors. With that will come new decisions. Do we keep relying on telescopes alone? Or do we stage rapid response missions, small spacecraft ready to sprint out and meet the next visitor? The idea sounds like science fiction, yet it is seriously being considered. The European Space Agency has already started on a mission concept known as Comet Interceptor. This mission, planned for launch in the late 2020s, will station a probe in space at a stable point in the Earth-Sun system to wait for a suitable target. The idea is that if a new comet is discovered, especially one making its very first approach to the Sun or even an interstellar comet like this one, the Comet Interceptor could be deployed to quickly travel to it and perform a close flyby, capturing images and data up close. It is a way of not having to start from scratch when an object is found. The spacecraft would already be out there, warmed up and ready to swing into action. While Comet Interceptor's primary plan is to target an as-yet unknown incoming comet from the distant Oort cloud, it is conceivable that an interstellar target could be attempted if one is discovered early enough and within reach of the spacecraft's capabilities. The challenge, of course, with true interstellar objects like 1I, 2I, or 3I is that they move extremely fast, and we usually detect them only when they are already well on their way in. By the time we have a solid trajectory, designing and launching a mission from Earth to catch up becomes virtually impossible with current technology. We would need either far more advanced propulsion or a lot more lead time. Some visionary engineers have proposed ideas like Project Lyra, a concept study exploring how we might send a probe to chase something like Oumuamua using high-speed rockets or gravitational slingshots. So far, such plans remain theoretical, but they underscore the point. If we truly want a hands-on examination of an interstellar visitor, we might one day need to be very clever and very quick. Another possibility is that we might get lucky. An interstellar object could, by pure chance, be captured into our solar system for a while. If one happened to pass near a giant planet like Jupiter at just the right speed and angle, it could be gravitationally snagged into a bound orbit around the Sun, at least temporarily. That would be the cosmic equivalent of catching a wild bird in a snare, giving us a lot more time to study it. The odds are low, but not zero. Some simulations even suggest it's possible a few objects currently orbiting the Sun, perhaps some unusual asteroids or comets, were originally interstellar but got captured ages ago and now masquerade as locals. Part of the excitement of identifying new objects is testing them to see if any fit that description. For now, what this interstellar visitor signals is that the cosmic ocean around us is full of driftwood, and we are finally getting better at noticing when a piece washes up on our shore. Each piece has its own story, and collectively, they tell a larger tale of the galaxies mixing and mingling. Let's pause from the narrative of discovery and place ourselves in the shoes of someone trying to understand an object like this one. How do we figure out what it is made of or where it came from, all from so far away? This is where a couple of big ideas in physics become wonderfully useful and can be explained in everyday terms. First, the magic of spectroscopy, the technique that allowed us to discern the comet's chemistry. Think of sunlight or starlight as a rainbow of colors all blended together. Now imagine that rainbow passing through a cloud of gas. Certain atoms or molecules in that gas will absorb very specific colors of light, like thieves stealing particular hues from the rainbow. If you spread the light out after it passes through using a prism or a diffraction grating, you will not see a perfectly continuous rainbow anymore. You will see dark gaps or lines where colors are missing. Those missing bits are like fingerprints. Each chemical substance has its own unique set of favorite colors it absorbs and also emits if excited. By carefully examining the spectrum of the comet's coma, scientists saw the fingerprints of water, carbon dioxide, carbon monoxide, cyanide, and other molecules. We do not need to bring a sample of the comet into a lab to know what is in it. The light that travels from the object to our telescopes carries signatures of its composition. It is a bit poetic that we can identify the chemistry of a world from another star just by splitting its light and reading the barcode of colors imprinted there. No sci-fi tricorder needed, just physics and a good spectrograph. Second, consider how gravity choreographs the journey of an object like this traveler. We often talk about gravity as a force, but it is equally useful to think of it the way Einstein described it. Space itself is like a flexible fabric, and massive objects, stars, planets, and so on, create dents or dimples in that fabric. When a smaller object, like a comet, comes flying along, it is like a marble rolling across a warped surface. Its path curves around the dents. If the marble is moving slowly enough, it might spiral into the dimple and get bound to it, like a planet captured in orbit. If it is going a bit faster, it might loop around once or a few times. That would be an ellipse, like a comet that returns periodically. But if it is moving really fast, above a certain threshold speed we call the escape velocity, it will curve around the massive object only slightly, and then continue on its way, not caught. That is exactly what a hyperbolic trajectory is. The comet comes in fast. The sun's gravity bends its path into a sharp curve, but not enough to trap it. The result is a one-time visit. No one needed to push the object away with a rocket. It was flung onto that path by gravitational encounters long ago. And the sun simply gave it a deflection, like a cosmic slingshot, sending it on a new course back out to the stars. There is also a subtle note about time. At the speeds it travels, relativity is not just an abstract theory. The comet is nowhere near fast enough for the effects to be dramatic. But even at tens of kilometers per second, clocks moving with the traveler tick a tiny bit slower compared to clocks on Earth. The effect is incredibly small, a difference of mere nanoseconds, but it is real. Our GPS satellites experience similar tiny time dilations due to their speed and the weaker gravity up in orbit, and they have to correct for them to give us accurate positions. It is mind-bending to realize, but even a comet passing quietly through the solar system experiences time just a touch differently than we do standing still on Earth. The universe never wastes a chance to remind us that space and time are woven together. Let's return to the comet itself and what we saw during its solar system sojourn. We know it is not enormous, at most a few kilometers wide, perhaps even as small as half a kilometer across. Thus, It is somewhere between the size of a Manhattan island and a small mountain. It is definitely not a skyscraper-sized monster, but a modest comet by solar system standards. In telescopic images, it looks like a soft puff of light, the nucleus hidden inside its halo of coma. Some observers with powerful telescopes reported a long, thin tail when the viewing geometry was favorable, and at times an anti-tail, a curious perspective effect where the dust trail from our viewpoint seemed to point toward the sun rather than away. This happens because of how the dust spreads out in the comet's orbital plane. From certain angles that spread out, dust can appear as a spike or tail on the sunward side, even though the dust itself is still drifting away from the sun overall. It is an optical illusion that many comets have displayed, and this visitor was no exception. As the interstellar comet neared its closest approach to the sun, the increased warmth led to subtle changes in activity. Observers noted a surge in brightness at one point, likely the result of a particularly volatile pocket of ice, perhaps a CO2-rich area, venting rapidly, a mini geyser on the surface unleashing a flurry of dust and gas, and briefly making the comet more luminous. Later, as it got even warmer, still not as warm as comets that dive very close to the sun since it stayed well outside Earth's orbit, water ice deeper in the nucleus began to sublimate more strongly, adding a greater amount of water vapor to the mix. The behavior was dynamic but within the bounds of what comet scientists expected. A general increase in activity as it approached the sun, possibly with a few bursts when fresh ice was exposed, and then a decrease as it receded and things calmed down. Importantly, the nucleus appeared to hold together. Some comets, especially small ones on their first passage near a star, disintegrate if heating and outgassing overcome structural integrity. We saw no evidence of a breakup, no sudden massive increase in brightness or fragmentation in images. It survived its solar encounter intact and simply carried on its way. In a sense, that fact too is a clue. It tells us the core likely has enough cohesive strength, perhaps more than a loose pile of rubble, to endure a bit of sunlight without falling apart. Scientists also use the window of observation to measure physical properties like rotation. By tracking periodic variations in its light, essentially the comet's flickering as it tumbled, they inferred a rotation of roughly every 16 hours. This is a comfortable spin rate, not so fast as to be on the verge of flying apart, and not unusually slow either. It is akin to many comets we know. The dust production, estimated from the brightness of the coma and tail, suggested it was shedding on the order of a few kilograms of material per second at peak activity, which sounds like a lot, but for a comet is quite moderate. Comets can range from less than a kilogram to many kilograms per second, depending on size and makeup. All these details, size, spin, activity level, gas ratios, dust characteristics, come together to form a portrait of the object. And in that portrait, we see something both exotic and familiar. Exotic because of its origin beyond the solar system, yet familiar in behavior and makeup. It is as if the cosmos is telling us that the recipe for comets might be similar, no matter which kitchen, meaning star system, they were baked in, with a few unique local spices thrown in. Where exactly did this traveler begin its journey, and how old is it? These are questions that tantalize astronomers and the public alike. When its discovery was announced, initial speculation about its velocity and trajectory led some to call it perhaps the oldest comet we had ever encountered, hinting that it might have come from a very ancient star system. There was talk about whether it originated from the Milky Way's thick disk, a component of our galaxy that contains many older stars, stars older than the Sun, possibly formed when the galaxy was young. If that were true, The comet could be an extraordinarily ancient wanderer, potentially formed 8 or 10 billion years ago, around a star that has since died or drifted far away. The possibility that we were observing a comet older than our entire solar system was thrilling and poetic. Tracing an object's path through the galaxy, however, is extremely difficult. Our galaxy is not static. Over millions of years, stars orbit the galactic center and move relative to one another. To hunt for its home, astronomers attempted to calculate the past trajectory through space and see if it might have come near any known star in the last few million or tens of millions of years. Using precise measurements from the Gaia Space Observatory, which maps the positions and motions of billions of stars, one team traced the path back about 10 million years. They identified dozens of nominal close encounters, instances where the comet might have passed within a few light years of a star. However, none of those encounters stood out as a definitive birthplace or ejection event. In each case, the approach was not close enough, or the timing was not quite right to conclude. Yes, that star kicked out the object. The analysis of its motion, particularly how it moves relative to the plane of the Milky Way, led scientists to lean toward an origin in the galaxy's thin disk, where our Sun resides, rather than the thick disk. The thin disk contains stars of many ages, including the Sun and younger, whereas the thick disk stars are generally very old. If the comet did come from the thin disk, its home star could be a Sun-like star, maybe somewhat older or younger than ours. That would suggest the object might be on the order of billions of years old, but not necessarily double the age of our solar system as the thick disk idea implied. In any case, whether from thin or thick disk, this body is almost certainly very old and has traveled far. It likely formed in the earliest era of its original solar system, as one of countless icy planetesimals, and spent eons in cold storage at the fringes before something set it free. That thought of a comet that perhaps kindled around a distant sun in an epoch long before humans, possibly before Earth itself existed, is deeply humbling. Consider this: long before humans walked the Earth, long before Earth even coalesced as a planet, there may have been a quiet star in a far part of the galaxy under which 3 IATLAS took shape. Around that star, comets like it circled in a dark cloud. At some point, a cosmic fluke gave this one a push. Now, after an almost incomprehensible voyage, it drifted across our sun's path and lit up our telescopes for a short while. It is as if a tiny emissary from a bygone era and a distant world dropped by unannounced, giving us a brief glimpse into a story that started light years away and ages ago. This traveler will not remain in our neighborhood for long. By early 2026, it will grow exceedingly faint as it heads back into the outer solar system and beyond. Soon after, it will slip out of reach of even our largest telescopes. It will continue on its journey, bound to the galaxy as a whole rather than any single star. Perhaps millions of years from now, it will pass near another star and briefly become that system's interstellar visitor. For us, once it is gone, it will likely never return. It will become like Oumuamua and Borisov before it, a memory and a collection of data in our archives. But its legacy will live on in multiple ways. First, the data. Astronomers have collected a treasure trove of observations during its visit. We have detailed spectra, revealing its chemical makeup, images of its dust coma and tail, measurements of its brightness over time and how it rotated, and very precise orbital calculations charting its path. All of this will be studied for years to come, even after the comet itself is a faint speck beyond Pluto. Scientists on Earth will pore over the information we gathered. Papers will be written describing its composition and behavior, comparing it to other comets. Those findings will feed into our broader understanding of how star systems might differ or resemble each other in their formation of small bodies. The data also helps refine our techniques. The next time another interstellar object appears, we will know even better how to observe it quickly and thoroughly. Secondly, this encounter is influencing mission planners and space agencies. It adds momentum to ideas like the rapid response missions we discussed. It provides a concrete example that will be cited in proposals. Look how much we learned from one interstellar comet with just telescopes. Imagine what we could learn if we sent a probe. It underscores that these interstellar visitors are not just rare flukes. They are out there, and we are starting to find them. Ignoring them would mean missing opportunities to study pieces of other star systems that have literally come to us. In the halls of astronomy conferences and space agencies, this vista will be remembered as a catalyst that strengthened the case for being ready to intercept the next one, or at least to improve our observational networks. Will we see another traveler like this again soon? Probably yes. Interstellar debris is common. We were mostly blind to it before, but now we are watching the skies with wide open eyes. With better surveys, we will catch more of these messengers. It might even happen within the next year or two, or perhaps it will take a bit longer, but it is likely only a matter of time. Each one will test our instruments and our imagination. Some could be small and faint, barely detected. Some might be larger or pass closer, giving us a better show. Some may be dustier and produce a noticeable tail. Others might be quiet and harder to classify. All of them will confront us with the same thrilling perspective shift, that our solar system is not an isolated island, but part of a vast cosmic archipelago, with bits of flotsam and jetsam washing up on our shores from time to time. There is also something profound in the realization that our solar system is not self-contained. We have long poetically described space as an ocean and stars as distant shores. Now we see that comets and asteroids are like boats or driftwood that can journey between these shores. Materials swap hands across the galaxy. A comet born around another sun can carry organic molecules, the stuff of chemistry that under the right conditions could lead to life, and drop them off in a new environment. In that way, interstellar objects might contribute to spreading the building blocks of life from one star system to another. It is a speculative idea, known as panspermia in its extreme form. But even without invoking life, it is awe-inspiring to realize that the ingredients for planets and maybe life are being exchanged throughout the Milky Way. A visitor like this reminds us that the story of Earth and the story of life here may include chapters that were written light years away. In some far-off future, we might even capture an interstellar object intentionally. Perhaps technology will advance to the point where we can alter the trajectory of a visitor slightly, just enough to put it into orbit around Earth or the Moon. Imagine having a captured comet from another star in a stable orbit, where we could send astronauts or robots to study it directly for years on end. It sounds like science fiction now, but so did landing on comets or bringing back asteroid samples not long ago. And those we have achieved. For the time being, the next best thing is to send our robotic emissaries to briefly chase these objects, or to scrutinize them with our telescopes as we have done. One day, holding a piece of another solar system in our hands might be within reach. For now, we do what we can. We watch carefully, we compare notes globally, and we build a collective understanding from a multitude of observations. We have become cosmic listeners, waiting for whispers from the stars. It is tempting when confronted with the unknown, to crave the spectacular, to hope that a mysterious object is a probe or a harbinger of something monumental. The genuine story can feel quieter, but it is deeper. This is a natural object, and yet it manages to be extraordinary. It is a messenger from a place we cannot reach, a scrap of a distant world carrying information to us by simply being what it is. It challenges our models of comet formation, pushes our observing technology to its limits, and even provides a perfect drill for our planetary defense systems, all without posing any threat. It reminds us that even in the stillness of a dark night, the galaxy is bustling with activity. And now and then a traveler wanders close enough to share a few secrets. As the sky's restful darkness returns to quiet and the traveler fades from our view, we know its story is not truly ending. The data gathered will keep scientists busy for years, extracting every bit of knowledge this visitor has to offer. Spectra, images, spin measurements, chemical analyses, orbital tracking, all of it will feed into the next cycle of research. Perhaps a graduate student right now will write a thesis on its peculiar chemistry, or a space agency will cite it as a reason to fund a new mission. In that way, the comet's visit will continue to inspire and teach long after the object itself is gone. If you find yourself outside on a clear morning in the coming weeks, look up and think about what is out there. The traveler itself will be far beyond the reach of your eyes, already receding into the black. But it is there, a faint whisper of light heading back into interstellar space, carrying dust and secrets from another sunrise that rose in a distant sky. It came to us, shared a little of its mystery, and moved on. We were lucky to witness it. Somewhere out there, the next messenger is already on its way, across the immense gulf of space, drawn by chance into the sphere of our sun. When it arrives, next year, in 5 years, tomorrow, who knows? We will be ready to listen to its story.